Hi everyone, welcome to this new episode of Astronomy on Tap London. As usual, stay-at-home version, and as usual, I'm hosting the event with Corentin. So hi Corentin.
Hello.
Today we are very excited about the topic we are going to discuss in a moment with our amazing speaker. But before introducing her, there is another important announcement. As you may know, the NASA rover Perseverance will land on Mars tomorrow, February 18th, and its main scientific focus will be finding out whether there was ever any life on Mars in the past. So for this reason, Perseverance will land in a crater where scientists believe there was a lake. So don't miss the NASA live event starting tomorrow at around these hours. It will be 7 p.m. GMT. This mission is part of a larger initiative to prepare for human exploration of the red planet. So stay tuned for very cool news in the future. And now let's get back to our event. Don't forget to follow us on our social media, you can see here. And also don't forget to subscribe to the YouTube channel. Let's introduce our speaker, Lucy Hogarth. She's a PhD student at UCL. And today, like a detective, she's going to kind of discover who or what turned the stars out in galaxies. Hi, Lucy, and welcome to Astronomy on Tap.
Hi.
But before getting into kind of this astronomical detective job, you started with a slightly different path, Lucy. So we are curious to know more about it.
Yeah, so I actually started as a art student a few years ago now. I was planning to study art at university, started applying. But I'd always loved physics and particularly astronomy, but I was never very good at maths as a kid. So I just assumed throughout my life that, okay, I can't do the maths, so I'll do art instead, which I also love. But I decided to give it another go, and so I taught myself how to do a maths A-level, and it went really well. So I thought, why not do astronomy in the end? And here I am. So it worked out.
Well, and we can see your talent in drawing, Lucy. I mean, I know it because we are in the same research group. I mean, it can be seen by your background. So yes, well done.
Yeah, I've been having fun with some virtual webcam stuff.
It's a bit less boring than mine.
So before giving you the screen, as you know, we usually post some questions before the live event on our social media, and you can go there on our one of our accounts to check them. But I would ask Corentin to introduce the questions, and we'll give the answers, or we will discuss the answers after Lucy's talk. And as well, you can post your questions during the talk and after in the chat box. So feel free to drop them there, and we'll answer at the end. So Corentin, the screen is yours.
Yes. All right. So we had two rows of questions coming from Lucy. The first one was who or what turned the stars out? And so this is like a question with multiple possible answers. The first one is all the gas has been used as fuel to form stars. The second possibility is that the galaxies that host the stars has collided with another galaxy. The third option is something has disturbed the environment in the galaxy where stars form, preventing them from forming. And the first option was, sorry, that was me, or that was Lucy, or that was anyone doing astronomy. So place your bets in the chats on this side, I guess. And we will discuss which ones are the actual answers to the question. The second one was like a bit of trivia to spot the differences between these two images. So these are two images from two observations of galaxies. And the question is, what are the differences? And how these different, well, these two galaxies have like forming a different amount of stars. And the question is, can we spot differences that give us clue about that? All right, well, I'm going to stop sharing my screen. Yep.
Thank you, Corentin. And well, if you cannot spot the difference, don't worry, maybe we cannot do it either. We'll find out at the end. Okay, so Lucy, well, the screen is yours and we are going to mute and shut the videos off because you're not going to share the screen.
Yeah. Okay, we are. Okay, so hello everyone. As has already been introduced, this evening we're going to be asking who turned the stars out. It sounds a bit of a strange question, right? But understanding how and why galaxies stop producing new stars is actually quite a mystery in a galaxy's evolution, and one where theoretical and observational astrophysicists like me have to work together. So, to approach this question, let's first have a quick recap on how stars form in galaxies. So stars form in dense, cold clouds of molecular gas. That's gas made out of molecules that would have been destroyed in hotter regions of the galaxy. Variations in density cause that gas to break up, like in my little diagram here, into smaller clouds and collapse under their own gravity. Once fusion starts in a new star's core, the surrounding gas is blown away from the star, creating very intense stellar winds. So the molecular gas we're talking about here is mostly molecular hydrogen. That's two hydrogen atoms stuck together, like in the three little diagrams up there. That gas is mostly found in the spiral arms of a galaxy, like you can see in the picture behind my head. It's where the gas is clearly denser and where most of the stars are. So although molecular gas makes up a small fraction of a galaxy's total mass, the amount of it actually determines how much stars it can make. So it's a crucial ingredient of a galaxy's composition. The dynamics of molecular gas, how it moves in and out of galaxies, can look a bit complicated. That's illustrated in the diagram on the left and more artistically demonstrated by my quilt version of the diagram on the right behind me. But the main features we care about, looking back at the diagram, is the gas falling into the galaxy, which is going along the blue arms where it says accreting gas, and also the outflows from the galaxy. That's gas leaving, which is in the diagram, the red gas, which is coming out of the top and bottom of the galaxy in the picture. So maybe this is a slightly easier way to look at it. So this jar represents what we call the equilibrium model, and it illustrates how molecular gas enters and leaves a galaxy. Molecular gas can move into our galaxy's gas reservoir via the inflow element, so the blue arrow saying gas inflow into our jar. So it moves into the gas reservoir via that element, and that's from the environment around the galaxy. From that reservoir, the gas can then be used to make new stars. So it moves from the blue area inside the jar into the red area, where it can create new stars, like the famous Orion Nebula, which I've got on the left here, which is a famous molecular cloud in our own galaxy, which is creating lots of new stars. So so it's moving from the blue area in that jar into the red. When a star dies, they release their gas back into that reservoir, so going from the red area to the blue back into the gas reservoir. And we can see that in objects like the Crab Nebula, which is depicted on the right behind me, which shows all the gas released from a massive supernova explosion. So all that colourful gas around it has been ejected from the star back into space. That gas can then be used either to make new stars, so going in a circle back into the red, or it can be expelled from the galaxy via the outflow element, where it says the red arrow, where it says wind outflow. There are a few ways that molecular gas can be expelled from a galaxy, which we're going to talk about in a moment. From the equilibrium model, it's clear that if either the inflow or outflow elements become unbalanced, the number of stars being formed in a galaxy would be greatly affected. So any increase in the available gas in that reservoir can lead to a burst of intense star formation because there's more gas to make more stars, effectively. A decrease in the available gas can effectively stop more stars being made, turning a star-forming galaxy into what we call a passive galaxy with little star formation. So my hand is invisible, but anyway, from the star-forming galaxy at the top of that diagram, spiral arms, to what we call a passive galaxy. And I think I've got a couple of real photos for you. There we are. So there's a couple of real images of a star-forming galaxy. On the left, lovely spiral arms with stars forming there. And then on the right, a passive galaxy, which tends to be to have less structure and has mainly old stars. It's not creating any new stars. So now let's have a think about the actual processes which can cause galaxies to quite literally run out of gas. The first process we're going to talk about is something called quenching. So imagine a scenario where a galaxy is taking in a lot of molecular gas from its environment, like in the where I've just drawn in the top of the diagram there. As a result, there's a massive burst of star formation because there's a lot more gas there. The intense star formation produces violent winds of fast-moving material, which can, in theory, and I'll explain why it's only in theory in a bit, expel molecular gas from a galaxy. This massively increases the outflow element of our equilibrium model and dries up the gas reservoir, meaning no more stars can be, or very little stars can be recreated. So if we just go back, so this quenching is effectively turning up this outflow element and draining out the gas reservoir. So here is a picture of what a sudden burst of star formation might actually look like. This is Messier 82, or the cigar galaxy, as you can kind of see, I guess. It looks a bit like a cigar, which is undergoing an intense star formation burst, which is powering those red outflow jets above and below. You can see there, so that's the sort of thing we're talking about. The other process of molecular gas depletion that we're going to talk about is the rather scarily named strangulation. It's not a nice name. So this is the process whereby we have a galaxy that suffers a sudden change in its environment, which stops the inflow element of our equilibrium model. So unlike the quenching, where we're talking about the outflows dialing up, we're talking about here the inflows dialing down, which also reduces our gas reservoir. Unlike quenching as well, stars will continue to be created for a while with the gas already in the galaxy, because unlike quenching, the gas isn't being stripped away. We just haven't got any more gas in the local environment for whatever reason. But eventually the star formation would die out and we'd end up again with a passive non-star forming galaxy. So strangulation is a little hard to show a real image of, but theoretically, a galaxy's inflows could be disturbed by another galaxy passing nearby, which could mop up all the gas in the area, or push the first galaxy away, or the gas away by gravitational interaction, which is what is happening here in these two images, where we've got galaxy pairs interacting, and you can see the gas being stripped out and disturbed. So strangulation could possibly happen in this sort of scenario. So you'd think we understand why, stars go out, right? It sort of seems clear, but it's not exactly that clear cut. We can model these scenarios pretty well, and the theory seems to kind of be quite logical, but there's actually very little observational evidence to support it. Quenching is particularly important in how we model galaxy evolution. For galaxies to regulate their star formation in the way that we think, molecular gas has to be driven out by those stellar winds that we talked about. Otherwise, molecular gas would continue to build up and up without any outflow element in our equilibrium model. And star formation would just continue to be more and more intense. And that's not what we observe. We don't observe that, generally speaking, in galaxies, that star formation just gets madly, madly out of control. It seems quite regulated. So if the stellar winds cannot drive out molecular gas, we need to come up with a new way to explain what we observe. So in truth, we don't actually know who turned the stars out. And in that spot the difference image, what actually you had is an image on the left, which is an object which has really intense stellar winds, which theoretically could be driving out molecular gas, and the one on the right doesn't have these stellar winds. So could those hold the difference? Is it that you have strong stellar winds which drives out the molecular gas? It's sort of an unanswered question. So how do we go about actually solving this problem? So as I said, I'm an observational astrophysicist, and I try and look for direct evidence of stellar winds moving molecular gas out of galaxies to try and prove that or disprove that theory. To do that, we obviously need to look at both the stellar wind and the molecular gas in galaxies. And well, that's not as easy as it may sound, or maybe it doesn't sound easy, I have no idea. But we need two kinds of telescopes, basically. One that can measure optical light to look at the stellar wind, and one that can measure radio emissions for the molecular gas, because they both emit light at different frequencies. You can't use one sort of telescope. So in my work, I use the Anglo-Australian telescope, which is depicted it's the top picture, which is in New South Wales, and also ALMA, which is in the Atacama Desert in Chile. ALMA's quite different looking to how I think most people would imagine a telescope. It's actually comprised of several satellites, I think 66, and those all act together to simulate a massive telescope of kilometers in size, which is necessary in order to see detail in radio frequencies. To finish off, I'm not going to go too much into what I've found, because I wanted to give more a taste of the background behind this work. But what I will say is that contrary to what is expected, that molecular gas would be thrown out by the stellar wind, what we've actually found is that galaxies that have a very intense stellar wind from high levels of star formation, actually the molecular gas seems to be more concentrated in the center of the galaxy, which is kind of the opposite of what you would imagine, and it's very weird. So it could be that the theory of the equilibrium model, our theories of galaxy evolution are flawed, and we'll need to come up with a new theory of how it actually works. But that's really what makes astronomy so interesting, is that things happen that you really don't expect. So I'm going to leave it there. I'll hand back to Chiara.
Thank you very much, Lucy. That was a very interesting talk, and well, with beautiful graphics. Well done. Okay, so in the meantime, post your questions in the chat, and we are going back at the questions we presented at the beginning. So, Corentin. Corentin, you're muted.
That's what I was wondering. So the first question was who or what muted me? No, sorry, turned the stars out. Well,
But
so
we can see the slides though.
Oh, what? Okay, yeah, good.
It works now, yeah.
Yeah, sorry. Sorry about that. So who or what turned the stars out? I guess so. Well, you mentioned all the possible events that do turn stars out. So maybe you can comment on that slide, Lucy.
Yeah.
So which are the correct ones? Enlighten us.
Well, actually, 1 to 3 are all right. The only wrong one is 4, unless, I don't know, you're some sort of celestial being, in which case you probably know the answer anyway. So, I mean, all of these possibilities could be true. So it could be that all the molecular gas has left the galaxy, so the fuel that the stars needs is gone. The galaxy's collided with another galaxy. That's what we were talking about with the strangulation potentially. Or something that's disturbed the environment, again, could be strangulation, that the gas has left the local environment. Yeah, so if you answered 1 to 3, you got it right.
Yeah, well, I do simulations, so I can also turn stars off if I decide to in my simulated universes.
That's true. I didn't think of that.
So I did answer 4, but that was a personal bias. Okay, and then the second question was like the spot the difference question. So which difference are we supposed to see on that images?
Well, I'd be quite surprised if you actually did see a difference. So these are 2 objects that I'm looking at in my work. They're both kind of edge on. So you saw in the pictures that I showed of a galaxy that actually had outflows, that they were coming out of the top and bottom. So that's why we look at galaxies which are kind of sideways on perspective wise to us. And the one on the left, I think, as I mentioned in the talk, the one on the left has massive, intense stellar winds. So lots of star formation powering, lots of material being moved away from the stars. On the one on the right, does not. So could these objects actually give us an idea of, do the stellar winds play a role? Is that what's driving the molecular gas out, or has it got nothing to do with it at all? At the moment, I'm not sure. As I said, it seems like the molecular gas could be doing the opposite of what we thought. So I don't know. Again, it's a slightly misleading question, as there really is no right answer.
How do you know that there are stellar winds? I mean, like, can you read that off these images, or do you need extra?
No, so the way we measure stellar winds is using the information from the Anglo-Australian telescope that I used, and there's a mission from atomic hydrogen, so not the molecular hydrogen, the cold gas we're talking about. This is atomic hydrogen, which is really hot and ionized. An emission from that tells us that we're seeing massive amounts of gas being ejected at high speeds away from the plane of the galaxy, so above and below.
Thank you, Lucy. We've got a question in the meantime. Is it fairly common for galaxies to merge across the universe?
Yeah, it is very common. And so the picture of the passive galaxy that I showed, the theories about how passive galaxies lose their structure and kind of just become round blobs is that over time they're just merging and merging over and over again with all these galaxies, and they just lose their structure over time and just become a fuzzy blob. So merging is actually quite a big part of a galaxy's evolution, and it happens all the time. Galaxies are not static things, they're moving, and they run into each other, and they're attracted to each other by gravity. So they're very much dynamic things.
And do you have any of these merging systems in the galaxies that you are studying?
Well, that's an interesting question. I mean, none of them look actively like they're merging, but it's possible that they could have merged in the past. And could that be a reason why the molecular gas is different in both of them, as they're more concentrated in the ones we thought that they should have been less concentrated? But it's possible that that could be a part of their history.
We have another question from the chats from Stephen King. And the question is, don't existing and dying stars return material into the interstellar medium? And why is that not in the balance model?
So it does in my, I don't know if I can put it back. Let's go through the slides. Oh, there we are. So in the model, you can see in the red area with the stars, there's an arrow going into and out of the gas reservoir. So gas can circulate from stars to the gas reservoir back again. The problem is that each time that happens, the gas is going to be getting heavier. So there's going to be more metal because the stars will have fused together a lot of what started off as just molecular hydrogen into much heavier elements. So it becomes harder for the stars to use that material every time. But that gas does circulate in the equilibrium model, certainly.
So Lucy, I had a question. You mentioned that in your research, in your sample, you found that the molecular gas is centrally concentrated. So what would be the next step, like the next observations that you would like to look at to find out more about what is happening in your galaxies?
Yes, that's a good question. So at the moment, what I'm looking at is instead of just looking at the distribution of the molecular gas, it's actually looking about how fast it's moving, and if those so we can look with the data we have at the velocity of the gas at different radii. So it's another way of looking if there's any sort of evidence of the ionized gas driving the molecular gases. There's similarities in where there are spikes in the velocity of our molecular gases with the ionized. I think in an ideal world, it would be fantastic to have a bigger galaxy sample because it's quite a small sample. It would be good to just have hundreds and then perhaps have a more concrete answer. But I think every observational astrophysicist just wants more data. So it's kind of a cop-out answer, really.
We have another question from the chat from Basil this time. And the question is, if galaxies attract each other, right? Why don't stars attract each other and collide?
Stars do attract each other, definitely. I mean, it's not really my area of stars colliding, but they certainly do attract each other into that. Binary stars are hugely common. I was reading somewhere that they may even be more common than single stars, maybe. So having stars which are gravitationally attracted to each other and rotating each other is super common. And as I said, it's not my area, but I'm certain they do collide with each other.
Thank you, Lucy, for the answers. So I don't see anything coming up in the chat. So yeah, well, I think we can close the event here. Thanks a lot, Lucy, for this fantastic talk. Again, don't forget to subscribe to the YouTube channel and well, take care and see you in 2 weeks. Bye.